Assalamu alaikum. Hello, everyone. This recording is to provide guidelines for the final project for ISE 291, Introduction to Data Science. So this will help students understand the different steps that are involved towards building the model for the final project. Okay, so we start with the first phase, the discovery phase. Okay, here you need to select your task or problem. Is it regression, classification, or clustering? So based on your choice for the task, you will need to find a relevant data set. So for example, if your task or chosen task is regression, then you need to find a data set where the target variable is a continuous valid variable. Okay. If it's a classification problem, then you need to find a data set where the target variable is a class label. If it's a clustering problem, then you need, actually here the objective is to reveal the underlying structure in the data and define the different clusters. So there is no target variable here. Then, yeah, you need to state, of course, your problem very clearly. So, for example, yeah, like your problem is a prediction problem. So based on like some input features, for example, here I'm giving an example, like given like this is a like house prediction task. So given the district, the area, the number of rooms, the number of bathrooms, and some other features, you need to predict the selling price of the house. So keep in mind, like here, your task, actually, you're building a model from the training data set. You're building a model. That model is a mapping function that takes, in the implementation phase, takes a sample with some features, okay, as an input, and produces a prediction for the target or the output variable. That's for the regression and for the classification. For the clustering, given a sample, you need to like associate that sample to one of the defined clusters. Okay, so then the second step is to go to the data cleaning and preparation. So here is the logical sequence, I believe, for the data cleaning and preparation phase. You start by fixing any inconsistencies in your data. So here I'm giving some examples to explain what do we mean by inconsistency in a data. So here are the first example, for example, this one, okay? So this is one of the attributes, okay? So assume you loaded your data and you created your data frame, and this attribute, population attribute, is loaded as an object, okay, because of the existence of this comma here. So this is supposed to be integer, okay? Then you need to fix this issue. You need to convert this from a categorical attribute to an integer or numerical integer attribute. Okay, this is an issue you need to fix. I'm giving some examples here, okay? For example, another example here, assume like for a certain attribute, okay, some of the records were collected using a unit and some others collected using a different unit. For example, here, this attribute is meant to be some distance between two places. So, okay, or points, okay. Some of the attributes, the unit that is used for those is centimeter, while meter is used as the unit for some others. Then you need to fix this issue. You need to bring all of them to the same unit, okay? So you have to change the unit. Otherwise, this will actually badly affect the performance of your model, okay? And there could be more examples for inconsistencies. I'm trying here to highlight some examples, okay? So then the next step is to do data cleaning and, to handle the missing data, okay? So, and the way you handle the missing data, okay? So for example, if you have like an attribute, okay, where like the data is missing for most of the entries, okay, for most of the samples, then maybe it's better you actually remove that attribute, you drop that attribute, okay? But like, for example, if the value for that attribute is missing only for a few elements, then maybe you can do imputation here in this case. And the type of imputation that you will implement depends on the type of the attribute itself. So if the attribute is a numerical attribute, then you may need to consider the mean or median imputation. If it's like a categorical attribute, then you may need to consider mode imputation. Then after that, you go to the next step, okay, which is removing outliers, okay. We have already went like through data visualization. So, and we know how to plot the box plot for every attribute. So we can actually visualize the statistics of every attribute. So we use box plots for that. So we plot the box plot for every attribute, and then we can visually see like if there are outliers, okay? If there are outliers, then we may drop them, okay? In some applications, outliers are noise, and it's better you drop them, otherwise they will badly affect the performance of your model. But actually, in some other applications, the outliers could be the thing that you are looking for. So things at the end of the day depends on your application, okay? So sometimes, as I said, they are considered as noise, then maybe it's better you drop them so they don't badly affect your model. And for some applications, maybe it's the thing you are looking for. So things, as I said, depends from your application. And here, in fact, for this project, you can actually try building one model without dropping the outliers and another model with dropping the outliers. And then you test the generalizability of these two models in your testing data. And then you can actually come up with a conclusion which one is doing better, okay? Then the step that comes after that is converting all non-numerical attributes to numerical attributes. And that depends from the type. So for nominal attributes, then you need to perform one-hot encoding. So you do not introduce an order that wasn't there to begin with, okay? And if there's an order, if your categorical attribute is of type ordinal, then you need to perform ordinal encoding. So you maintain the order. You need to maintain the order, okay? Now we come to the next step, which is normalization. So you need to perform normalization, okay? There are different techniques in order to perform the normalization. We have explained this in the lectures. We have min-max, z-score, and scaling. In min-max, actually, we are bringing every feature to be in the range between 0 and 1. So the minimum is exactly at 0 and the maximum is exactly at 1. And for the z-score, or we also call it standardization, we are bringing every feature to be centered around 0. So the mean is equal to 0 and the standard deviation is equal to 1. Okay, so this brings all the features, min-max, brings all the features to the same scale. They all start at 0 and end at 1, but z-score is less sensitive to outliers. So if you did not remove the outliers in the previous step, you may consider doing z-score normalization, okay? And there are two reasons why we do normalization, okay? The first reason is we actually, okay, let me explain it by example. Assume like you have two features. One of them it's coming from one-digit numbers, so between 1 and 10, okay? And the other one is like from three-digit numbers at thousands, okay? Now you don't want the one that is coming from high values to dominate just because of the high values, okay? So then you need to normalize both of them, bring both of them to the same scale, okay? That's the first advantage or the first benefit we get from the normalization or scaling, okay? The second thing is like, if you look into this figure here, these are like, this is the contour of the loss function, okay? So this is like, we assume here two features, okay? If they are not scaled, then this is the kind of contour we will see, okay? If one of them is coming from high values and the other one is coming from low values. Then we usually, when we train, we are running iterative algorithms. We start with the initial guess and we're moving towards the optima, okay? So here, the movement is a bit hard. It takes more time to converge and it may oscillate a lot. Versus here, this is like both of them are scaled, so the contour is more of a circle and the movement towards the optima is much more smooth, and it could actually be much faster. Okay, so that leads to faster conversions. So just I mentioned min, max, and score. This scaling is like feature scaling, like for example, divide by the max. Okay, that's one way to scale the features down. Okay, one final thing to mention here in this slide: if your task is regression, I would prefer, if the task is regression, I would prefer to normalize all the features as well as the target variable. Okay, we normalize the target variable as well. But be careful here. Later, when you run your model, what you are predicting is the normalized version of your target variable. So you need to reverse that operation in order to deliver the exact value. Okay, and that is actually more important if you do min, max, and z-score normalization, because actually here they are not only simple scaling. Okay, they involve subtraction here. Okay, so then you need to actually normalize both the input features as well as the target variable. Okay. Now we come to the exploratory data analysis. This actually what was provided in the guidelines you have regarding the exploratory analysis. What I believe, most of these are not really needed towards building the model. They are maybe good to go through this if you are doing data summarization, or if you are studying like the effect of one variable in the statistics of another variable in general, or if you are like looking like doing some statistical analysis to one of the input variables. But actually, towards building the model, they are not really, these are not so important. Let me explain. Okay, so I came up actually with this example. For example, in one of the lectures, we explained, like, for example, here, we are plotting the statistics of the reading score, which is a numerical attribute differentiated by the value of another categorical attribute, which represents the test preparation course, whether it's taken or not, completed or not. Okay. So with this, we can see clearly the effect of taking the course in on the statistics of the reading score. So in average, it's better to take the course. Okay, so the median here is higher, and we avoid the outliers from the bottom. Okay, so we can infer that kind of information. Okay, this is good for this kind of information, but towards like making predictions for a given sample, we want to predict an output, this analysis is not really important for that. Okay, so what I believe is important is what's coming next. So the first important thing is to actually compute and plot the correlation map. You compute the correlation between all the features, okay, and between every feature and the target variable. This is important. Okay, why that's important? Because this actually tells you which features are correlated to the target variable, which are the most correlated ones, or the ones that are strongly correlated, and which ones are weakly correlated or uncorrelated or irrelevant. Okay, so you can define those. Okay, so then actually, for example, these two here, they are weakly correlated. You can actually exclude these two. Okay, you just focus in the highly correlated ones. Okay, there is one thing I want to mention here. As the number of features increases, the number of samples you need in order to train the model increases exponentially. So if there are irrelevant features, sometimes it's better to remove them because they may lead to the problem of overfitting. You have many features, so you are trying to actually fit so many features with a limited number of samples. So you will run into the problem of overfitting. So we want to avoid that problem. So that's why sometimes you need to actually get rid of the weakly correlated features or the unrelated or irrelevant features. Okay, so you can remove them manually like this, and we're going to come to other options later on. The other plot that is important, okay, is sometimes a scatter plot. Why is that? Because actually correlation, and specifically the type of correlation we teach in this course, Pearson's correlation, can capture the linear dependency. So it can actually capture any linear relationship between any of the input features and the target feature, as well as any relationship between different features. Because as I said, if there are features that are correlated to each other, then maybe there is a room for dimensionality reduction here, and we can drop some. So we actually look at the correlation between the features as well as the correlation between every feature and the target variable. But again, correlation can capture the linear dependency, okay, the linear relations, okay, the linear relationships. But actually, it fails to capture the non-linear relationships. Therefore, maybe you plot the scatter plot to see if one feature is actually non-linearly related to the output. Then maybe for that specific feature, you can actually consider higher orders for that. So you go from x to x squared, for example, x cubed, okay? Maybe log x, depends on the relation you see, square root of x, okay? So then scatter plot can be useful here in this case to capture any nonlinear dependency, and you may include higher order features. I don't know for the level of 291, do we really need to go to that, but I'm explaining this. So if you want to make it interesting, then you may need to consider this, okay? You may consider higher order like degrees or higher order polynomial degrees of the sum of the features. So the model is still a linear combination of all of these features, but the relationship between y and some of the input features will not be linear anymore, because some of the features are higher degree polynomials of some of the existing features, okay? So that is that's where the scatter plot is useful, okay? So if you wanna actually, now we are moving from linear regression to polynomial regression, okay? As I said, maybe you wanna be just biased towards linear relation for the project of this course, that's fine, okay? But if you wanna make it more interesting, you can actually go beyond that, okay? So here, but don't go too much in the higher degree polynomials. Here, I'm just giving an example. Here, for example, if you are biased towards the linear relation, as you can see, these points are more fit with non-linear curve. So we may need, so I'm assuming here one feature versus the target variable. So if we are biased toward linear relationship, so we're not really, it's not really linear, but that's the best we can do if we are biased just towards linear relations. So we are considering only like the feature x. Here, if we are going like to x squared, then we are moving beyond the linear relation. We are coming up with a curve, okay? And it seems here we are doing really a good job. These are the training data, the red ones. So we are actually approximating the relation very well here. Here we are actually introducing more higher order polynomials, but we are running into the problem of overfitting here. We are so much concerned about what the training data is telling us, so we will not generalize well outside our training data. So we will do bad for the green points here, okay? I don't want to go so much into those details for this course, but yeah, hopefully the idea is clear, okay? Then we go to the model planning, okay? So here so from here onward, I will explain like the model planning and the model building in the context of regression problem, okay? So you may consider in the model planning, you may consider these three options for regression problem. So you may consider all features, okay? You don't throw any of the features. You rely on the regularization, okay? Because for Ridge and Lasso, you have actually weighted sum of two terms, okay? The term which we have already an ordinary least square, which minimizes the difference between the predicted variable and the actual value, okay? The predicted value and the actual value. And we also have actually, yeah, so here, I don't want to go there now, okay? So we know this, okay? So let me just be very brief here because the details are gonna come later on. So the option one is you consider all of the features, you don't throw any of them, okay? You rely in the regularization, in the regularized term, okay? To kill or bring the weights of some of the features to be low, okay? And that's what we do when we introduce the regularization in Ridge and Lasso regression versions, okay? That's one option. You can go with that option. The other option is actually you manually remove the weakly correlated features as we did here, okay? You could remove these features from the beginning and you still can actually run three models, okay? Or less, Ridge, and Lasso. and you see like which one is performing the best for the remaining set of the features, okay? So you remove the weakly correlated features to the target variable, okay? The option 3 is to perform principal component analysis. So here we are in both of these cases, we are actually reducing the dimensionality of our data points, because remember, every data sample is a point in the n-dimensional space where n is defined by the number of features. So here we are reducing the number of features, then we are actually reducing the dimensionality. So in both cases, we are reducing the dimensionality. Here we are removing some, manually we are removing some of the features. Here we also do dimensionality reduction, but here now for option 2, we are left off with some of the original features we have. But here we are actually moving to a new set of features. Every one of these features is a weighted sum of the original features. It's a linear combination of the original features, okay? And we can perform that dimensionality reduction. We compress the number of features, okay? So we can, for example, keep the number of principal components such that X% of the variance is covered. X could be 98, 97. So that could be achieved by keeping only the, for example, the first 4 or 5 principal components. Then we just keep only those, and we build a model based on the principal components, those principal components. So this is, again, as I said, sometimes it's good to perform dimensionality reduction, because actually, as I said, as you include more features, then the number of samples you need has to grow exponentially with respect to that. So if you have a limited number of samples, then maybe it's better you compress, okay? And also to avoid overfitting, okay? So you can actually build models for this, like with these 3 different options. I think, yeah. So yeah, one thing, so you will divide your data into training data, validation data, and testing data. Yeah, we're coming to that actually in the next slide. That was the model planning. Now we come to model building. As I mentioned, we split the data into training, cross-validation, and testing sets. Then we train the different variants of linear regression in the training data set. So each one of them has a different cost function or loss function, as we can see here. So we train each one of them using the training data set. So here h of xi is the predicted label, the predicted value. So here it's a regression problem. So it's the predicted value of our variable. So it's y hat of I. So it's a linear combination of the input features. It's a linear combination of all input features if we are considering option 1. If we have removed the weakly correlated features, then it is a weighted sum of the remaining features of the features that we are considering. If we have performed principal component analysis and we pick the first n principal components, then it's a weighted sum of those chosen principal components. And if we have performed like higher order transformation for some of the features, we introduced higher degree polynomials for some of the features, then it's a weighted sum of the original features plus the higher degree polynomials of the sum of the input features. So in that case, y hat is still, it's a weighted sum of these features. It's a linear combination of these features, but it's the relationship between y and some of the features is not linear anymore. Okay, in the case if we considered, as I said, higher degree polynomials for some of the features. Okay, then actually we are moved from linear regression to polynomial regression. Anyways, so let's assume, as I said, let's consider, let's go back to what, to what we are doing here. So we are considering these 3 variants of linear regression, and we are training them on the training data set. So we will train every one of them. So let's assume, okay, I should have actually put alpha 1 here and alpha 2 here, just to mention that they could be different, okay? So anyways, let's assume that we start and let's actually follow this. We start with low value for alpha, and we train these three. And after we train them, we actually measure the training error. For the training error, we only consider this term here. We don't consider the regularization term. Okay, so we don't consider that, even for this algorithms. So when we want to measure the training error, so we don't consider these. Okay, we consider them when we train. So once we converge it to a set of model parameters, okay, then we compute the training error. The training error involves only this term here for the three choices. Okay, so we measure the training loss, then we validate each one of them in the validation data set. Okay, now as I said, we started with low value for alpha. Okay, assume we are achieving a good training loss here. Okay, after, as I said, we measure the training loss or the training error. Let's call it the training error, okay, because this is the loss function for every one of them, but the training error for every one of them is this. Okay, so we trained each one of them for that choice of alpha, and we converge it to a set of a set of model parameters, and we measured the training error. Then we actually validated each one of these models in the validation data set, and we found like that the validation error is very high compared to the training error. Then in this case, what happens is that because alpha is very low, then the weight of the regularization term is very low compared to this term. So this is almost zero. So then we care only about fitting our data, our training data. So we get so much concerned about what our training data samples are telling us. So that's why we're performing good here, but we're not generalizing well outside this training data set. This is the problem of overfitting. So we run into the problem of overfitting here. Then what we do, we go back, we increase the value of alpha, and we train again. We will converge to a new set of the model parameters. We measure the error here in the training data set. The error may increase, but then we validate it in the validation data set. If we found like our model is generalizing better outside the training data set, then actually we are maybe this is a better choice than what we had previously, because our model is able to achieve lower loss on unseen data. So we keep iterating between these two until we converge to the best set or choice for the model parameters as well as the hyperparameters. Then we actually test our model on the testing data. So the testing data should not be used to learn the model parameters, and it should not be used also to fine-tune or learn the hyperparameters. It's just used to test the generalizability of our model, how good our model in generalizing outside the training data. Okay, so then we report that error, the generalizability error. Same steps here we did here can be applied for option 2, where only we consider for option 2 and 3, where only we consider the we manually kills and weakly correlated features. Okay, so we still can also perform these 3 variants and test them and do the same steps. For option 3, where we consider the top principal components, we may not need to introduce regularization here, because actually we are considering the very related, I would say, features in that sense, in that in that specific option. So here just then you communicate the results, you provide a summary and conclusion of your analysis and any possible future recommendations. So for the operation, you need to provide general guidelines to adapt your model or methodology, and you need to list any issues of implementation. Okay, let me talk a little bit more about this. You remember, so for the training, you remember, like we started with the whole data, and we performed like some transformation and normalization. So now when you move to operation mode, every sample you receive, you need to perform the same kind of transformation and normalization before you feed your sample to the model. Okay, so you either like give those like steps to the customer, or somehow you build the the complete software that takes whatever the input sample is and perform all this transformation and normalization before feeding to your model. And if you have normalized the target variable as well in your before you train, then what you are estimating or predicted is the normalized version of your target variable. Then you need to reverse that step at the end. Okay, as I said, it should be either part of your software or part of the instructions that you give to the customer in order to run your model. So let me remind you of that. So you remember in the training, we used to normalize the input features as well as the target variable. So we have computed this min and max from the whole data before we split it into training, testing, and validation. So this, we need to maintain these values. The min and max, we need to maintain them because we need to use, we need to always relate to them. We don't compute a new min and max. So we need to store them, okay? So here we used to take an input feature, we normalize it, and here the example I'm making here is an example of min-max normalization, but the same idea applies to whatever kind of normalization you do. So here in the training phase, we used to normalize using min-max. We used to normalize both the input feature as well as the predicted variable. So now in operation phase, you will receive only X, okay? The input features. You don't know Y, you are predicting Y. So then you need to normalize your X using the same variables here. You need to subtract the same min computed at the beginning and the same max. So you need to subtract the min and divide by max and min in order to compute max minus min, sorry, in order to compute the normalized input features, and then you feed the normalized input features to your model. What you are predicting here is the normalized target variable. It's the target variable, but it's normalized version. Okay, so what you are predicting, because your model, remember here, your model is trained to take normalized input feature, predict normalized output. So you're passing here normalized input feature, so you will predict the normalized output. Then you need to reverse that operation. So you need to move from the normalized output to the exact value of the output. So you need to multiply the normalized output with max minus min, and you add the min. So then that's what you're going to deliver as the output of your model. Okay, with that, I came to the end of those guidelines. I hope you find them useful. Thanks for watching.